We're going to go through Lewis dot structures, named after Gilbert Newton Lewis. And first thing that I mention here is that when you go to draw the structure, sometimes it's hard to tell what to do, and one approach to figuring out the right approach is by drawing orbital diagrams. And so in this particular example with water, I've started with the orbital diagrams here. And let me fix this. Somehow that got weird. And here are the orbital diagrams. And what you'll see is an unpaired electron here, 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 and here. And often when you see that, that's the right way to know where to make your covalent bonds. And it looks a little odd, but this bond here and this bond here correspond to my boxes that I have made here and here. And so sometimes this can help. Now, the normal way to do Lewis structures is what's called the total valence method. And that's how you're typically taught to do this. So when you do the total valence method, if you find that you're having a hard time figuring out what to do, try the orbital diagram and it may sort things out. When doing the total valence method, make sure that you're careful that every bond is 2 electrons. Often when students draw molecules incorrectly, it's because they're not subtracting 2 electrons from the total as they draw their molecules. Now, in regular chemistry, if you were to run into an odd number of electrons, that means you made a mistake, something's wrong. However, it is a possibility that we have to address now. If this happens, the most electronegative atom will get the octet, and the less electronegative atom is the one that loses out in this situation. So looking at this example down here with NO, this one, nitrogen contributes 5 electrons, valence electrons, of course, oxygen 6 for a total of 11, and that is what we have to work with. So if you start at the beginning, it looks like this. We've got nitrogen bonded to oxygen, and of my total 11 electrons, I've used 2, so now I have 9. I always like to start with the more electronegative atom. So what I would do is I go, okay, oxygen needs 6 more. 1, 2, 3, 4, 5, 6. Subtract that. I now have 3. I'll give those to nitrogen. 1, 2, 3. I'm now out of electrons. Oxygen's happy. Oxygen has the 8 that it needs. Nitrogen has 1, 2 from the bond, 3, 4, 5. So, okay, we can help out a little bit here. What we can do is we can take a pair from oxygen, doesn't matter which pair I choose, make another covalent bond, which gives me this. Oxygen still has 8. Nitrogen now has 7. Because 1, 2, 3, 4, 5, 6, 7. And that's the best we can do. So to remind you, when you have to pick who is the more or less electronegative atom, one way is just to look at the periodic table. And because nitrogen is to the left of oxygen on the periodic table, you can basically assume nitrogen is less electronegative. The other way is to actually look up a chart of electronegativities and sort that out, which is why when I give an exam involving these topics, I usually give a periodic table that shows the electronegativities, just so students can be confident. Now, the result is this. And because nitrogen only has 7 electrons in its outer shell, it's said to be a deficient octet. And that's referring to the nitrogen. Oxygen has the normal octet situation here. Going up above, I mentioned polyatomic ions. What you do with polyatomic ions is you have to add extra electrons if the charge is negative, and you subtract if the charge is positive. And so I'll show that in this example here. I'll clean things up. And do this example. So if we want to do phosphate, you see my list of atoms. I have phosphorus with 5, oxygen, 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 and then you must account for this extra charge of -3. So that's 3 more. So it gives you a total of 32. So start with phosphorus, make it symmetrical. I've used up, of my 32 electrons, I've used up 8. And then notice phosphorus is already satisfied with an octet, and every oxygen needs 6 more. So 6, 12, 18, 24. And if you work out the math, we're now done. It works out really nice, makes sense. Put this in brackets to show that the entire thing has an extra 3 electrons, which matches what we have. Now this concept here that NO has paramagnetism, we'll cover that more in a future lesson. Right now we don't really need to deal with that. To the next page. If you take a look at carbon dioxide, this is a perfect example for what we're about to deal with. You can draw it this way with 2 double bonds, or you could draw it this way with a triple bond and a single bond. They both make sense. Everybody has an octet. If this was first year chemistry, both are acceptable. One way to tell what happens is to use symmetry. This structure on the left is more symmetrical. And normally symmetry will win out. But the better way is to do what's called formal charge. And I have it listed here. You put the number of electrons that have been contributed by each atom from their valence shell, and then you subtract the number of electrons that have been acquired in your particular drawing. So if we look at the left version, oxygen contributes 6 every time. I'll also look at the right version at the same time. Carbon contributes 4. That's going to be the same no matter how you draw it. The acquired is how I'm going to look at what's in the drawing. So if you look at the left drawing, this oxygen here, it has 1, 2, 3, 4 that it owns. And then the double bond, you give it half of what's available. So there's 4 electrons in the double bond, but you only give it 2 of them. So that adds up to a total of 6 electrons that it has acquired. It gets 4 from the unpaired electrons, and then it gets half of what's in the bond, which is another 2. So that's 6. Carbon, clean this up a little here. The carbon, it only gets electrons from bonds. So it gets half of the 8 electrons in the bonds, and that's why it gets 4. The oxygen on the right here is the same as the oxygen on the left, and that's why it ends up with the 6. You subtract this from what they contributed, and what you will see happens is that it works out to be a 0, a 0, and a 0. And that's what you're looking for. That's good. A formal charge of 0 is desired. Let's compare this to the one on the right. If we look at the oxygen here, it has 1, 2, 3, 4, 5, 6, plus half of what's in the bond, which would be 7. So that's where the minus 7 comes from, and you get a negative 1. Okay, now let's look at carbon. The carbon still is getting all of its electrons from the bonds, and half of the 8 electrons in the bonds is the minus 4, so it ends up as a 0. Looking at the right oxygen, it has 2 electrons that belong to it, 1, 2, and then the rest of the electrons come from the triple bond, so it only gets half of that. So of the 6 electrons in the triple bond, it only gets 1, 2, 3. And so that's a total of 5. That's why I've got a minus 5. When you subtract that from 6, you get a plus 1. Now comparing these, the version on the right has a negative 1 formal charge on the left oxygen and a positive 1 formal charge on the right oxygen, and that is not as good as what we have on the left, in which everybody has a formal charge of 0. And that's why, if you have to pick between these two options, the version on the left is better. That's why I labeled it the winner. Going to this next example, if you go through the steps, you will find that nitrogen ends up with the deficient octet with 7. Both oxygens end up with an octet. And you also end up with resonance here. What happens is when you draw this structure, you have a choice. Do you want to put the double bond on the right side or on the left side? Well, since they're equal, neither is preferred, and so the correct answer is actually both of them. Now, the way you would answer this on an exam is you would say O and O with, of course, the appropriate dots. You would draw the other version. You'd put a double arrow between them to show resonance, and that's how you would show it on an exam. But I don't really want you to think of it like that. That's not what it really is happening. A better way to think of it, but it's hard to draw, and don't do it this way on an exam, would be to show something where this shows the electrons that belong to each atom. And then to show the resonance, you can kind of think of it as being something like the electrons sometimes are here and sometimes are here. So you wouldn't draw this, but it's a good way to think about the way the molecule actually exists. Because this term resonance makes you think the double bond is snapping back and forth between these two spots. And it's not really doing that. The double bond is not snapping back and forth and oscillating. It's just that the electrons are sometimes over here and sometimes over here. I want to talk about a term that you'll see that comes up every now and then. And this is delocalized. If electrons are said to be delocalized, that means they don't belong in one exact spot. So these electrons here, we'd say that they are localized. They belong to that oxygen. These electrons here, we'd say are localized. They're being shared between these two. But delocalized means that they're being shared among numerous places, like the ones that are happening in resonance here. Next topic, internuclear distance. Sounds kind of scary. So inter, between, nuclear, the nucleus. In other words, what is the distance between the atoms? Well, the best way to look at this is by looking at this diagram that I have here. If we were to try and put two hydrogen atoms really close together, the protons in the nucleus would repel each other, and that's why it's too close. The protons would repel each other, the electrons in their orbitals would repel each other, and that just would not be a happy situation. It's way too high in energy. Likewise, if you get them too far apart, you don't have repulsion. The nuclei are not going to repel, and the electrons in their orbitals aren't going to repel, but you can't share electrons now. This space is too big for these two atoms to share electrons in a covalent bond. And so what results is this situation here, in which the atoms are close enough that they can share electrons in this single covalent bond, but their nuclei are not so close that they're going to repel too much, and the electrons in their orbitals of separate atoms are not going to repel each other. And notice this is lowest in terms of energy. You'll notice I mentioned bond length, otherwise known as the distance between two atoms, will be influenced by both the size of the atom and what's called bond order, or whether it's a single, double, or triple bond. If you have a double or triple bond, the atoms have to get a little bit closer than normal to share extra electrons. And so you'll find something like, some examples here. If we were to compare H2, O2, and N2, I'll leave off the extra unshared electrons. You would find that N2, the atoms are going to be closest, and H2, they will be further apart. So the farthest apart, based on the sharing of electrons in the covalent bonds. All right, I have an example here with sulfur trioxide. And it's a pretty common example that you'll see when doing problems. Sulfur trioxide and sulfur dioxide is a really common example of resonance. Just clearing up my board here. And this question poses an interesting scenario. It says a sulfur oxygen single bond is 9 nanometers, but a double bond is 3 nanometers, which makes sense. Okay, the double bond's closer based on the discussion that I just had. So why is it that in a SO3 molecule, the SO bond is 7 nanometers? Well, what you have to factor in is the resonance. This double bond is resonating, and it's being shared among all 3 of the oxygen atoms and the sulfur in the middle. And so you just take an average. So based on my drawings here, if I just stop the molecule for a moment, so just pick a single version, I'll pick this one on the left. The sulfur oxygen double bond will be 3. The sulfur oxygen single, 9. The other single will be 9. Divide that by 3 items, and you get a total of 7 nanometers average. And this, as I mentioned here, is an example of how we know that resonance is actually happening in real molecules.